today, we couldn't just multiply any two probabilities. What had to be true? They had to be independent events. So knowing one didn't change the probability of the next one. Now, if they are not independent events, things kind of change. We have what are called conditional probabilities that show up. So when you see something like this, that means the probability of F given that E has already occurred. Okay, so it might be that I am going to randomly pick a student out of this class to come do the next example. Okay, how many students are in here? 10 right now. Okay, so if I randomly pick one, the probability of you getting selected is 1 in 10. What if I tell you I'm going to pick a male student to do the problem? Yeah, now it's a 1 in 2 chance. So the probability changed. Knowing that I was going to pick a male changed the probability of being selected. So that is a conditional probability. So here's an example with the dice. So if I roll a 6-sided die, what's the probability of getting a 4? 1 in 6. Now, let's say I rolled a die up here, and I said I rolled an even number. Now what's the probability of getting a 4? 1 in 3. So that is an example of conditional. Given that you knew it was even, it changed the probability that it would be a 4. When we find conditional probabilities, I think on your formula sheet, if you look at it, it has these and it has a couple options listed. So we are now on the back of the first page. So the probability of F given E is the probability of E and F, the probability of both things occurring, divided by the probability of E, which is the condition that we already knew. And it also works when you're dealing with complements. The probability of not E and F divided by the probability of not E would work. So this is our formula for how to find a conditional probability. Let's take a look. To me, this is one of those formulas that it's almost easier just to think about the problem instead of trying to plug things into a formula. So a survey was conducted in which 1,017 adult Americans were asked about their beliefs in a higher power. So we have the responses broken down by geographical region and how they answered. What is the probability that a randomly selected adult American who lives in the East believes in God? Okay, how many people do we have altogether? And I said, but when I looked at this, am I looking at everybody? No. So if I was just asking you for the probability that a person from the East believed, then it would be out of everybody. But that's not how I phrased it. I said the probability that someone who lives in the East. So I already know they live in the East. So am I looking at all 1,017 people? No. I am only looking at these people because I already know something. When you have a conditional, it's changing your denominator here because I no longer looked at everybody. I already know it's somebody from the East. How many people were from the East? So my denominator is going to be 255. Then out of those, how many were from the East and said they believed in God? So now we have to start paying close attention to the words. If I said lived in the East and believed in God, then it would be very different because then it would have been out of everybody. But I knew they were from the East, so I was only looking at those people. All right, now I'm going to flip the question. What is the probability that a randomly selected adult American who believes in God? So what do I know? It's somebody that believes. So my denominator is only out of those people. How many are there? And from those, how many were from the east? So we get 0.2592. Right, so when you have a conditional probability, your condition is your denominator. Those are the only ones we're looking at. Is that okay with everyone? So let's look at this one. In 2005, 19% of all murder victims were between the ages of 20 and 24 years old. Also in 2005, 16.6% of all murder victims were 20 to 24-year-old males. What is the probability that a randomly selected murder victim in 2005 was male, given that the victim is 20 to 24 years old? So I'm trying to find the probability male given 20 to 24. So if you think about your formula that we have, general probability, or conditional probability, sorry, that's the probability of E and F. So that's the probability of male and 20 to 24 divided by the probability of E, the probability of our condition, which is that they are 20 to 24. So when the second piece of your conditional is the given, that's what you know, and that's what goes on the denominator. All right, do I know how many were male and 20 to 24?
16.6.
Okay, so I'm going to say 0.166. Divided by how many were 20 to 24? 0.191. You get 0.8691. So, this formula that we're using, if I took that, I could multiply my probability of E over, and then I would have a formula for an and, just like we were dealing with yesterday. So, if the probability of the first and the second happening, probability of E and F, is the probability of E times the probability of F given E. Or it could be the probability of F times the probability of E given F, depending on which one you knew. This is what we can do for, it's called the general multiplication rule because it works in any situation. More specifically, we're using this for dependent events. Because our definition of independent events are two things that have no bearing on one another, right? So the probability of one thing given that the other already occurred. So the probability of F given E. So the probability of you eating a chicken patty today, given that I wore black shoes. Are you going to be more likely to eat a chicken patty because I have black shoes? No, does that have any bearing on it whatsoever? So if they're independent, the conditional probability is the same as the regular probability. It didn't change even if we knew this other fact. So yesterday we were looking at those independent events. We didn't see this conditional because it didn't matter. One thing didn't change the other. But if they do have an impact, then we have to pay attention to that. Let's try some examples of this. So, from the same example that we were just doing, what is the probability that a randomly selected murder victim in 2005 was a 20 to 24-year-old male? So, I am asking you, to find the probability of male and 20 to 24. So we can use a couple different variations of this, depending on what we have. Do I have the probability of just being a male? No, so I have to do the probability of being 20 to 24 times probability of being 20 to 24 given. Oops, I flipped that. Times probability of being male given they were 20 to 24. What is the probability of being 20 to 24-year-old? Um, 191 were between the ages of 20 to 24. And we just found on the last example, probability of being a male given they were 20 to 24 was 0.166. So it's really, these can get confusing just because there's so many numbers. Strongly recommend, we're kind of at the point now where writing out your formulas is going to help you. Then you'll see what you have and where you can plug things in. Let's look at another one. Suppose that of 100 circuits sent to a manufacturing plant, 5 are defective. If the manager receiving the circuits randomly selects 2 and tests them, if they both work, she will accept the shipment. What's the probability that she rejects it? Okay. Is it going to be easier to find the probability that she accepts it or that she rejects it? She accepts it if they both work. She would reject it if they both are bad, or if the first one's bad and the second one's good, or if the first one's good and the second one's bad. So which one would be easier to calculate? The probability that she accepts it, because there's only one scenario where she accepts it. To find the rejects, you can certainly do it, but you have to do all 3. Now, how does it help me to find the probability that she accepts it? Then you can do 1 minus to get the probability of rejecting. Okay, so let's find the probability that she accepts it. Okay, so what makes her accept it? They both work. So the probability the first works. Now, if the first one works, does that change the probability that the second one works? We have 100 circuits, and there are 5 bad ones in my box. Okay, so if I take out a good one and set it to the side, is it a different probability that I'll draw a good one the next time? Yes, because there's no longer the same number to choose from. I didn't pick it up, look at it, and stick it back in. I set it off to the side. So I need the probability that the second works given the first one worked. Or if we just think about this, what's the probability that the first one works? How many good circuits are there? 95 out of 100. Okay, if I took out 1, how many good circuits are left? Out of how many total? 99. So we get 0.902. So then how do we find the probability that she rejects? So we get 0.098. So 9.8% chance that it will get rejected. All right. Any questions on that one? Let's look at this one. Of 3,215 individuals surveyed, 130 agreed with a recent bond issue. Supposedly, we randomly select one. What's the probability he or she agreed with the bond issue? So what do we do? No tricks, this is a straightforward one. If two individuals are selected, what's the probability they both agree? So what's the probability the first one would agree? 130 out of the 3215, or you could do the decimal. All right, if I've already talked to one person that agreed, how many people are left that agree? Out of how many total people? Be 14 now, because we already talked to one of those. .0016. What would we call that type of probability? It's unusual. Be very unusual to select two people that agree. In fact, it would even be unusual to select one person that agreed, since it's less than 5%. Okay, compute the probability of two individuals agreeing, assuming independence. If they're independent, that might mean there are two of us that we're going to go ask somebody. So I go ask somebody, and then Brian goes and asks somebody. Is there a chance that we could talk to the same person? Yes. So they're independent. Who I talk to does not change who he talks to. So what would I do in that case? So that's the probability that I talk to someone who agrees. What's the probability that Ryan talks to someone who agrees? The same. What do you notice about them in this case? Yeah, if we did more decimals, they are really not the same. But to 4 decimal places they are. And that has to do with the population size here. In general, if your population is big enough, you kind of get to assume things are independent.
She wants you to email her your thoughts on the books.
Okay. So if our sample is less than 5% of the population, we will treat them as independent. That's really not going to be relevant right now. It's more going to come into play in a couple chapters, but I figured I would go ahead and throw it out there while we were talking about it. All right, I want you guys to try this example. Let's look at it. So a computer chip company just shipped 10,000 computer chips. Unfortunately, 50 are defective. So part A, compute the probability that 2 selected chips are defective. So what's the probability the first one's defective? Okay, then using conditional, so that means I took it out, set it to the side, what's the probability the next one's defective? And what did you get?
2.4532.
Oh, at the very end it has e negative, so that tells you to move your decimal back. So what was e to the negative? Okay, so extremely unlikely getting two defective ones. I'm using independent events, so that might mean I check them at one spot and then somebody down the line checks it again. Could we look at the same chip? Yes, because I didn't set mine to the side. I looked at it, set it, put it back. So then the probability of the first one is 50 out of 10,000. Second one, 50 out of 10,000. And what's that give you?
2.5.
So move your decimal back 5 places, so 0.000025. So slightly more likely, but not much of a change. And that's just because we had 10,000 of them and a very small portion were defective to begin with. All right. Last problem of the day. These types of problems all come back to just using formulas. There's really no reasoning involved here. So the probability of A is 0.7, probability of B given A is 0.4. Find the probability of A and B. So what we should do is write down the formula we're doing. The probability of A and B is the probability of the first times probability of the second, given that the first already happened. So we plug in what we have. Probability of A is 0.7 times probability of B given A is 0.4. And what do we get? This time I have the probability of B, probability of A and B. I'm looking for A given B. So you notice, if I just go with the same formula, A and B equals probability of A times the probability of B given A. Does that help me? No, because I want A given B. So the other way I told you, we can flip this and make it probability of B times probability of A given B. So that's the version we're going to use. Basically just flip the A and the B. So the probability of A and B is 0.4. Probability of B is 0.5. Times probability of A given B. So if we divide, probability of A given B is 0.4 divided by 0.5. This one, I have A, I have B, I have A or B. I need A given B. If you look at your formula sheet, is there a single formula that involves all of that stuff? No. So if I'm looking, my formulas with A given B, that's the AND formula, right? Probability of A and B. So if you look back on the first page, the last thing, the general addition rule. Probability of E or F, so the probability of A or B. Probability of A plus probability of B minus probability of A and B. So we're going to start here. We know A or B is 0.6. A is 0.4, B is 0.3. We subtract over the 0.7. Divide. So what we found is probability of A and B 0.04. now what formula can we use? So if you think, we need the probability of A given B, so we'll have to do the probability of B times the probability of A given B. Do you guys understand how I'm picking my and formula and flipping my A's and B's? So basically for your conditional, when you do the and, whatever your given is, has to be the other probability you multiply by. So if I want B given A, I have to take it times probability of A. If I want A given B, I have to take that times the probability of B. Here I had probability of A given B, so my given is B, so the other probability I have to multiply by is B. So if we plug in A and B is 0.04, B is 0.3, times probability of A given B. So if we divide, probability of A given B is 0.1333. This last one. What does the line over the top mean? You guys remember? It's another way of saying the complement. So you might have it with just the little c, or you might have a line over the top. So the complement we know is the opposite. So here's all the stuff I'm given. How would I find the probability of B? 1 minus the probability of not B. You get 0.6. Probability of A. So what can we do? I don't have the probability of not A. Do we have any formulas that would involve the probability of A and the things that we do have? So there's a couple formulas that have the probability of A and B in it. One of them is, if we know they're independent, we can multiply. But did I tell you they were independent? So we can't assume that. So that means the probability of A and B here would have to be the probability of A times the probability of B given A, or probability of B times the probability of A given B, since I didn't tell you they were independent. So I don't have all those pieces yet. But could I use my general addition rule? Probability of A or B equals probability of A plus probability of B minus probability of A and B. A or B is 1. Probability of A we don't know. Probability of B was 0.6. What's the probability of A and B? 0.7 is the probability of not A and B, so be 0.3. So we get the probability of A is 0.7. So now if I want A given B, and we have a couple different variations, but probably the easiest would just be here. Probability of A and B, we said, was 0.3. Probability of B, we found to be 0.6 times the probability of A given B. So if you divide your 0.6 over, probability of A given B is 0.5. So this is just practice, kind of getting used to the formulas and solving with them. Questions? So that's my stopping point. Problem number 29 tells you you have to do a tree diagram, and you do not, unless you just really want to. So that picture is